What is so special about this particular sequence of numbers? If you're not sure, then you can pause to find the pattern. But if you are, then that's great. This over here is called the Fibonacci sequence. And the way it works is that the first two terms are 1, and then each next term is just the sum of the previous two terms. So 1 plus 1 is 2, and then over here, 3 is equal to 1 plus 2, and then 5 is 2 plus 3, and so on. Now you might be asking, what's so special? I could have set the first one to be 1 million. Like, what's so special about just starting with 1? Well, the reason that this sequence is so beautiful is because it happens to contain the golden ratio within it. Essentially, if we call the nth Fibonacci number Fn, and then we take the ratio of it to the immediately previous term, so Fn minus 1, then as n gets larger and larger, so I'll write n approaches infinity, as n gets larger and larger, this ratio converges towards the golden ratio, which is approximately 1.618, okay, approximately. Now, the golden ratio in math is denoted by the Greek letter phi, okay? And the golden ratio can be written exactly as 1 plus root 5 divided by 2. And this ratio is found everywhere. It's found in nature, it's found in art, it's found in music. It is one of the most beautiful ratios out there. And this sequence is so beautiful because it happens to contain this ratio within it. However, did you know that this beautiful sequence of numbers is also involved in counting and probability? Right, that's right. The world of combinatorics also contains this particular sequence of numbers. I'll show a problem that seems completely random, but the numbers it generates are the Fibonacci numbers. So here is the problem. Consider this staircase with 10 steps. On each turn, we may only move 1 or 2 steps at a time. So, how many different ways are there to reach step 10? So, for instance, we could walk just 1 step the entire journey, or we could take 2 steps the entire journey, or we could actually do a mixture, like 1, 1, 1, and then 2, 1, 1, 2, and then 1. So, any of those sequences would work. So, how many ways are there to climb up to step 10? Seems a bit complicated, right? However, when we have way too many staircases to deal with, our trick is to deal with simpler cases. What if there was only 1 step, or only 2 steps? That's more manageable. So, we're going to define a term, Tn, to be the number of ways to reach step n, okay? So imagine this 10 was replaced with n instead. So what would Tn be? How many ways are there to reach step n? Well, we're going to consider something simple, like T1. T1 is really easy. If you want to only reach step 1, then you can only take 1 step, right? So imagine this entire staircase disappears and there's only step 1. Then you can only take 1 step, obviously, so T1 is equal to 1. Okay, now imagine adding step 2, okay? Now, T2 is what we're calculating. For T2, this is also very easy. You can either move 1 step 2 times, so 1, 1, or you could just move 2 steps just at one go, right? Just move 2 steps. So there are 2 ways. T3. T3. What is T3? Well, you can brute force count it for yourself, and you'll see that there are actually 3 ways. You can do that for yourself, okay? Now, what about T4? Seems like the numbers are starting to get a little bit out of control. 4 is a little bit more complicated to count compared to 1, 2, and 3. Thankfully, when we start to get a little bit complicated, that's when we should start looking for a pattern, okay? So, think about this. I want you to think about the step right before you reached step 4, okay? Now, the step that you were on right before you reached step 4 had to have either been step 3 or step 2, right? Because you could only move 2 steps or 1 step at a time. So your second to last step had to have been on step 2 or step 3. Now, let's do some casework, okay? Case number 1. Let's say that your second to last step was on step 2, okay? So second last was on 2. If your second last step was on step 2, then your last move is fixed. You have to move 2 steps in one go to get to step 4 on your last step, right? Now, this would mean that your last move is fixed. So it doesn't matter what your next move is when you reach step 2 as your second last step. All that matters is how many ways were there to get to step 2 in the first place. Well, there are T2 ways. I know that's 2, but I'm going to write T2 to generalize. So this case would actually yield T2 ways, okay? T2 ways. Now, we're not done our casework because we have one more case to deal with. What if your second last step was on step 3, right? So case 2 is that second last step is on step 3. Well, similarly, if your second last step is on step 3, then you have to move one step, okay? Your final move is again fixed. So all that matters is how many ways were there to get to step 3. Well, again, there are T3 ways. So this would be T3. Again, writing this to generalize. So altogether, the number of ways to reach step 4 is T2 plus T3. You add the cases. So altogether, that is 2 plus 3, which is 5. Now, this looks suspiciously neat, okay? Because we've seen over here that T4 is equal to T3 plus T2. 2, 3, 4. That's interesting. This might suggest a very neat pattern. Indeed, if we were to instead now generalize for Tn, so not just for T4 now, we're going to generalize for an arbitrary n. If we were to consider Tn, and similarly here, if we consider the cases of whether your second last step was on step n minus 1 or step n minus 2, then notice that if your second last step is on step n minus 1, then your next step is fixed. Your next move, is fixed. You have to move one step. So it just matters how many ways are there to get to step n minus 1. Well, that's Tn minus 1, right? And similarly, if our second last step was on step n minus 2, again, your last move is fixed. Just move two in one go. So the number of ways to reach step n minus 2 is Tn minus 2. So if you add the cases, this suggests that Tn is equal to Tn minus 1 plus Tn minus 2. And would you look at that? We've built a recursive formula, meaning we're able to get each next successive term based on the previous 2 terms. Now this is very neat, because now, what are we looking for? We're looking for T10. So we can just calculate this. So T4, well, we know T4 and T3, so T5 is equal to 8, T6 is equal to 13, and T10, this would be equal to 89. So altogether, there are 89 ways. Now, firstly, I want to say that this is a very powerful problem-solving technique. Building recursive formulas is a very common tactic in counting and probability. Now, I promised that this problem has a connection with the Fibonacci numbers, and here it is. If we consider the recursive relation that we've built, Tn is equal to Tn minus 1 plus Tn minus 2, then if we were to compare it to the Fibonacci numbers recursive relation, that's Fn is equal to Fn minus 1 plus Fn minus 2, they're the same. Now, if we were to take the values of T1 to 10 and F1 to 10, then if we compare them, you'll see that they're the exact same values. However, there is one difference. What's supposed to be F3 is actually T2, right? This is F3 and this is T2. And what's supposed to be F4 is actually T3. So we see that the index values is off by 1. We can write this as Fn plus 1 is equal to Tn. So that's the difference. And the reason for this difference is because here T1 was 1 and T2 was 2. But the Fibonacci numbers was defined off of F1 is equal to 1 and F2 is also equal to 1. So that's what caused this shift in the index. But other than that, we see that the Fibonacci numbers is literally everywhere. It's now involved in counting and probability. They're actually counting something. And I think this is just so cool. One thing you discover in math just appears in like every other subject, and that's so cool. So I hope you found this video very interesting. I hope you learned a new counting technique, and I hope you just, again, found this very interesting. If you did, please do consider dropping a like and subscribing. Thank you.